Hello! In this video, we are going to prove the following theorem. Suppose a1, a2, an is a list of positive real numbers. Then the arithmetic mean of this list is greater than or equal to the geometric mean of this list. Now, we have already proven that the AMGM inequality holds for lists of length 2. That is, we have already proven the following fact. Suppose capital A and capital B are positive real numbers. Then capital A plus capital B over 2 is greater than or equal to the square root of capital A times capital B. So really, we're trying to generalize this. And before we actually get into proving this theorem, we're actually going to prove, in particular, that the AMGM inequality holds for all lists whose length is a power of 2. Specifically, we are going to first prove for all positive integers n, we have for all lists of positive real numbers of length 2 to the power of n, the AMGM inequality holds for that list. And since we're trying to prove a statement about all positive integers, we're going to use induction. So let's start with the base case. In the base case, we're trying to show that this is true in the case where n is equal to 1. So really, we want to show for all lists of length 2, the AMGM inequality holds. But that's precisely what this fact tells us. So the base case is already done. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n, and we assume that this is true for that arbitrary positive integer n. So we're assuming for all lists of length 2 to the power of n, the AMGM inequality holds. Well, the whole goal of the induction step at this point is to show that this is also true for n plus 1. That is, we want to show for all lists of length 2 to the power of n plus 1, the AMGM inequality holds. So let's give ourselves an arbitrary list of positive real numbers of length 2 to the power of n plus 1. And we want to show that the AMGM inequality holds for this list. Now, first of all, we can break this list up into two lists whose length are both 2 to the power of n. Here's what they are. These are both lists whose length is 2 to the power of n. Right, of course this list has length 2 to the power of n, but how do we know that this list has length 2 to the power of n? Well, we know that 2 to the power of n plus 1 is equal to 2 to the power of n plus 2 to the power of n. As you can imagine, this list goes plus 1, plus 2, and so on and so forth, up to plus 2 to the power of n. So yeah, this list has length 2 to the power of n. And because these lists are both length 2 to the power of n, the induction hypothesis applies to both of them, which means the AMGM inequality holds for this list, and the AMGM inequality holds for this list. And to say that the AMGM inequality holds for this list means this And to say that the AMGM inequality holds for this list means this. So now, we want to show that the AMGM inequality holds for the list we have here, which is of length 2 to the power of n plus 1. If we can show that, that will complete the induction step. So, to show that, well, let me write out the arithmetic mean of this sequence. Since we're running out of room, I'm just going to move back up to the top. So this is the arithmetic mean of our list of length 2 to the power of n plus 1. And to start, we know that 2 to the power of n plus 1 is equal to 2 times 2 to the power of n. So I'm going to pull a 1/2 outside of the fraction. Right? Just like that. But now, we're going to rewrite the numerator by emphasizing the sum of the first 2 to the n terms, and then the sum of the last 2 to the n terms. Basically, it's what we have in these two numerators. So these would be the first 2 to the n terms. These would be the last 2 to the n terms. But then a property of fractions is that this entire fraction is just equal to this guy over 2 to the n plus this guy over 2 to the n. But then we know that this guy is greater than or equal to the 2 to the nth root of this. And this guy is greater than or equal to the 2 to the nth root of this. And it follows that this entire thing must be greater than or equal to 1/2 of this guy plus this guy. But now notice, we have something of the form capital A plus capital B over 2. So we can apply this fact. If we take capital A to be this guy and capital B to be this guy, well, we have that capital A plus capital B over 2 is precisely what we have here. And it must be greater than or equal to the square root of capital A times capital B. And so this entire thing must be greater than or equal to the square root of this times this. So just like that. But then, notice we have the 2 to the nth root of this times the 2 to the nth root of this. Well, we can apply the following property regarding roots. If we take capital A to be this guy, and capital B to be this guy, and capital N to be 2 to the power of n, well then this entire thing is just the 2 to the nth root of all of this stuff multiplied together times all of this stuff multiplied together. But then, another property of roots that we can apply here is this. So let's note that since the outermost root is a square root, we technically have a 2 here. So applying this rule, we take capital A to be a1 times a2 times dot 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 times a sub 2 to the n plus 1. We take capital M to be 2 to the n and capital N to be 2. Then this entire thing is equal to the 2 times 2 to the nth root of a1 times a2 times dot 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 times a sub 2 to the n plus 1. But 2 times 2 to the n is equal to 2 to the n plus 1. And so we have shown that the arithmetic mean of our list is greater than or equal to the geometric mean of our list. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. And what we have just proven by mathematical induction is that the AMGM inequality holds for all lists of positive real numbers whose length is a power of 2. In other words, we have shown for all positive integers n, we have for all lists of positive real numbers of length 2 to the power of n, the AMGM inequality holds for that list. So at this point, we haven't even entered the rounds of proving what we want to prove. We have proven a completely separate statement. But now, let's actually focus on proving this theorem. Now, what this theorem is saying is for all positive integers n, we have for all lists of positive real numbers whose length is n, the AMGM inequality holds. Well, to prove that statement, we are going to assume for a contradiction that statement is instead false. So really, we are assuming that there exists a positive integer n naught such that we have a list of positive real numbers whose length is n naught such that the AMGM inequality does not hold for that list. Now, with this assumption, we are going to show for all positive integers n greater than or equal to n naught, there is a list of positive real numbers of length n where the AMGM inequality does not hold. So, since we're trying to prove a statement about all positive integers greater than or equal to n naught, we're going to use induction. So let's start with the base case. Now in the base case, we're trying to show that this is true in the case where n is equal to n naught. So really, we want to show that there is a list of positive real numbers of length n naught where the AMGM inequality does not hold. Well, by our assumption, we already know that we have a list of length n naught where the AMGM inequality does not hold. So the base case is done. So now, let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer n greater than or equal to n naught, and we assume that this is true for our arbitrary positive integer n. And the whole goal of the induction step is to show that this is also true for n plus 1. That is, we want to show that there is a list of positive real numbers of length n plus 1 where the AMGM inequality does not hold. Well, since we know that there is a list of length n where the AMGM inequality does not hold, let's call that list a1, a2, all the way up to an. And since the AMGM inequality does not hold for this list, this means it is not the case that the arithmetic mean of this list is greater than or equal to the geometric mean of this list. We must instead have that the arithmetic mean of this list is less than the geometric mean of this list. Now remember, the whole goal is to find a list of length n plus 1 where the AMGM inequality does not hold. Well, we're going to construct that list right now. The first n terms in that list are going to be a1, a2, ... an. The n plus 1th term of the list we're going to define to be this value. So we are going to show that the list a1, a2, ... an plus 1 does not satisfy the AMGM inequality. That is, we're going to show that the arithmetic mean of our list from a1 to an plus 1 is less than the geometric mean. Before we move back to the top, let me just write some notes up here. Now remember, we want to show that the AMGM inequality does not hold for the list a1 through an plus 1, where an plus 1 is defined to be this value. Well, first of all, since an plus 1 is equal to this, which is less than this, we have that an plus 1 is less than this. And since an plus 1 is less than this, well, we know that these guys are both positive. So if we raise both sides of this inequality to the power of n, the inequality remains the same sign. So we have that an plus 1 to the power of n is less than a1 times a2 times ... times an. And then, since an plus 1 is positive, if we multiply both sides of this inequality by an plus 1, we get an plus 1 to the power of n plus 1 is less than a1 times a2 times ... times an plus 1. And then a property of roots, if you recall, tells us if we have two numbers greater than 0, one less than the other, well, if we take the n plus 1th root of both sides of this inequality, the sign will remain the same. So this is what we get. So now, let's show that the AMGM inequality does not hold for this list. I'm going to first write out the arithmetic mean of this list. Which is this. And I'm going to replace an plus 1 with what it's equal to. And then, to get rid of the fraction we have here, we're going to multiply both the overall numerator and overall denominator by n. Well, multiplying n in the denominator just gives us n times n plus 1. And multiplying n in the numerator, well, we're going to have n times all of this. And then we have plus n times this. Well, the n's will cancel out, so we're just left with a1 plus a2 plus ... plus an. So, this is what we get. But notice, we have the same thing. So, if we factor out a1 plus a2 plus ... plus an, we're going to get this, right? As you can imagine, if we were to expand this out and expand this out, both the numerators would be equal. And so we see that the n plus 1's cancel out, so we're just left with a1 plus a2 plus ... plus an over n. And this is equal to an plus 1. And as we mentioned before this, an plus 1 is less than the n plus 1th root of a1 times a2 times ... times an plus 1. And so, we see that the arithmetic mean of our list is less than the geometric mean of the list. So, the induction step started out by assuming there exists a list of length n where the AMGM inequality does not hold. And we just showed that there exists a list of length n plus 1 where the AMGM inequality does not hold. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. And what did this induction show us? It showed us, for all positive integers n greater than or equal to n naught, there exists a list of positive real numbers of length n where the AMGM inequality does not hold. And remember, we are still working under the assumption that the theorem is false, right? And we're trying to reach a contradiction. So where does this contradiction come into play? Well, if you recall, for all positive integers n, 2 to the power of n is greater than n. Well, in particular, n naught is a positive integer, so 2 to the n naught must be greater than n naught. And we know for all positive integers n greater than or equal to n naught, this is true. So since this statement works for all positive integers greater than or equal to n naught, then in particular, it must work for 2 to the n naught. So taking n to be 2 to the n naught, we have that there is a list of length 2 to the n naught where the AMGM inequality does not hold. I'm going to call that list L. But now, let's go back to the first statement that we proved. We know that this statement works for all positive integers. So in particular, it must work for the positive integer n naught. So taking n to be n naught, we have for all lists of length 2 to the power of n naught, the AMGM inequality does not hold, right? And since this statement works for all lists of length 2 to the power of n naught, then in particular, it must work for the list L. Therefore, the AMGM inequality holds for L. So, the AMGM inequality does hold for L, and the AMGM inequality does not hold for L. So we've reached a contradiction. Our assumption that the theorem is false led us to a contradiction, so we must instead have that the theorem is true. And so this completes the proof. And so yeah, that's pretty much it for this video.